welcome back. In this video, we're going to determine whether this set W is a vector space. The set W is the set of all ordered pairs of the form x, 2x, where x is just any real number. And we're going to use the standard ordered pair addition and standard scalar multiplication of ordered pairs in R2 as our two operations. So what we have to do is verify that all 10 of those vector space axioms hold for this set W. If they all hold, then W is a vector space. But if only one of them fails, then we can conclude that W is not a vector space. So let's start with the first axiom. The first axiom says that for any two elements of the set, U and V, U plus V has to also be in the set, and that is called closure under addition. So what we have to do is check for two arbitrary elements of W. So we can't use specific elements of W. So my two arbitrary elements are going to be R, 2R and S, 2S. Those are two arbitrary elements of this set. And when I add them together, I just add them by component. Each component, corresponding component, is added. So it's R plus S is the first component, and 2R plus 2S is the second component. And if I rewrite that second component as 2 times the first component, it's clear that that is an element of the set W, because we have x in the first component and 2 times x in the second component. So it's closed under addition. The second property is commutativity of addition. So two arbitrary elements U and V, if we add them together, U plus V is going to be the same as V plus U. So we have to verify that for two arbitrary elements of this set. So let's do it with R, 2R and S, 2S. When we add those together, we get R plus S, 2R plus 2S. And because each component is just a sum of two real numbers, R plus S is just a sum of two real numbers, and we know that's commutative, I can rewrite the components as S plus R and 2S plus 2R. And now I can rewrite that as the sum S, 2S plus R, 2R. And that shows that U plus V equals V plus U. So addition is commutative. All right, let's look at the third axiom. This is the associativity of addition axiom. So if we add two vectors V plus W and then add U plus V plus W, that it should be the same as first adding U plus V and then adding W to that. So let's do that with three arbitrary elements of our set W. So let's use R, 2R and S, 2S plus T, 2T. So we're adding S, 2S plus T, 2T first, and then we'll add the R, 2R to that. All right, so I just added the S, 2S and the T, 2T together, and now I'm going to add R, 2R to that. So I get R plus S plus T, 2R plus 2S plus 2T. And now we can use the associativity property of addition of real numbers to write the first component as R plus S plus T, and the second component as 2R plus 2S plus 2T. using the associativity property of just real number addition. And now we can rewrite that as the vector r plus s, comma, 2r plus 2s, plus the vector t, comma, 2t. And the first vector can be split up into r, comma, 2r, plus s, comma, 2s. And all of that is going to be added to t, comma, 2t. And now we've just shown the associativity property. And so the third axiom holds. All right, move on to number 4. The fourth axiom says that there exists an additive identity in this set. A 0 vector is in this set. We have to identify it. Well, it turns out that the 0 vector in R2 is also in this set because we can write it as 0, comma, 2 times 0. So that's definitely in our set W. And clearly, if we add it to any arbitrary element of W, it acts like the identity element, the additive identity element. And we can add it in either order. So that axiom holds. All right, the fifth axiom says that additive inverses exist for every element of this set. So if we take an arbitrary element of our set W, we should be able to identify an additive inverse for that element. And that means another vector we can add to it to get the 0 vector. So let's pick an arbitrary element. And clearly, the only thing that'll work is negative r, comma, negative 2r, because when we add those two things together, we do get the 0 vector. So that means negative r, comma, negative 2r is the additive identity for r, comma, 2r. So that axiom holds. All right, let's move on to number 6. Number 6 says that the set is closed under scalar multiplication. If we take an element u from the set W and we multiply it by some scalar c, we're going to get something else that's in the set W. So let's pick an arbitrary element of W, multiply it by an arbitrary scalar, and scalar multiplication means you multiply each of the components by that scalar. And if we just rewrite that second component as 2 times the first component, we can see that clearly has the correct form, and that is an element of our set W. So that axiom holds. All right, let's move on to number 7. Number 7 is the the distributive property. One of the distributive properties, we've got 2 of them. This distributive property says that scalar multiplication distributes over vector addition. C times, so C is a scalar, C times the sum of 2 vectors, u and b, is equal to the sum of cu plus cb. So let's pick some arbitrary vectors in W, so add them together, and then multiply that by C, and let's see what we get. So it's going to be C times the sum of those 2 vectors, and now scalar multiplication says we can bring that C in and multiply each component by that scalar. Okay, so now I can distribute because I now have just a real number addition and multiplication. And so C distributes across that addition and across this addition. And now I can rewrite that as the sum of two vectors. The first one is CR, comma 2CR, and the second one is CS, comma 2CS. And now I can pull the C out, the scalar can come outside the ordered pair. And now we have what we wanted. We have the sum of C times the first vector plus C times the second vector. So the seventh axiom holds. All right, let's look at the eighth axiom. So this is another distributive property. This says that scalar multiplication or vector, the vector distributes across the scalar addition. So we can add two scalars together and multiply a vector by that sum, and that's the same as multiplying the vector by the first scalar, multiplying the vector by the second scalar, and then adding those two vectors together. So C plus D times the vector u is going to be the same as C times u plus D times u. It's another distributive property. So let's see how this works. So we have an arbitrary vector or an element of W, and we're going to multiply it by the sum C plus D, sum of two scalars. So the scalar multiplication operation says bring that sum, that scalar inside, and multiply each component by that scalar. So C plus D times R, comma C plus D times 2R. And now inside that each component of that ordered pair, we just have real number addition and multiplication, which is distributive. So the first component is CR plus DR. The second component is C times 2R plus D times 2R. And now we can split this up into the sum of two vectors. It's CR, comma 2CR plus dr, comma 2dr. And it's commutative because we know real number multiplication is commutative, so I'm rewriting it as 2dr so that it's in the right form. And now the scalar can come outside on each vector. And that's what the property says. So the property holds. All right, let's look at the last two. So the ninth axiom is another associative property. So if you first multiply a vector by D, you get another vector, and then multiply that vector by C, it's the same as first multiplying the two scalars together, C times D, and then multiplying the vector by that scalar. So let's see how it works on an arbitrary vector with two arbitrary scalars. So we take an element R, comma 2R. First, we're going to multiply it by D, a scalar, then multiply that by C, another scalar. So let's see how that works. So it's going to be C times this vector. So I first multiplied by D. Now I'm going to multiply by C. So after I multiply by C, it looks like this. CDR, comma CD2R. And now, clearly, we've got one scalar, CD, multiplied by each of the components, so I can just pull that scalar CD outside of the vector. So it's CD times the vector R, comma 2R. So that works. And then the final axiom says that we have a multiplicative identity, and it is the scalar 1. So let's multiply an arbitrary vector by the scalar 1 and see what happens. So multiplying by the scalar means multiplying each of the components by that scalar. And because this is just real number multiplication, we know that 1 times r is just r, and 1 times 2r is just 2r. So we have 1 times u is equal to u, so that axiom holds. All right, since we've verified all 10 axioms for this set W with these two operations, vector addition, scalar multiplication, and they all checked out, we can say that W is, in fact, a vector space. And that is the end of that proof. And I'll see you in the next video.